All right, so today we have a homework assignment due on the bi-tree CS, composite state pattern. So let's run through a few of these slides for methods for destruction and removal, and then we'll see if there's any, we'll field some questions, and maybe I can give you some hints. In fact, there's one hint that I know I want to give you. So methods for destruction and removal. Clear is I think this is a method for you to do. So first of all, clear is void, so we don't have to return anything, right? So basically what's going to happen is that the tree version is going to call the node version, and if the node version is the empty node, there's nothing to clear because it's already empty. The only thing you have to clear is if it's not empty. So here's the in figure 8.39 is a little picture of what happens if we are not empty and how we do the clear. Okay, so in part A of the figure, this is our original tree, and in the environment of a non-empty node, owner is a parameter. Are you with me? So that's part of the environment. So we have owner, and so owner's underscore head points to us. And then what we do is, in order to make the owner, now here's where the state comes in, the state pattern, because we have nodes. Okay, and we have access to the owner. Now what we have to do is we have to give owners underscore root. We have to have it point to the empty node. So do you understand that that's going to involve doing a new? Are you with me on that? And here is where the magic of automatic garbage collection comes in. Without shared pointers, the programmer would have to manually and individually clear the left subtree and clear the right subtree and clear the root. But with the magic of automatic garbage collection, we are done. The left and the right subtrees are automatically garbage collected, as well as the node itself. All right, and now I have a little hint for you on rem root. Now, it's not too obvious how the logic should be for rem root, because do you remember what was the precondition for rem root?
That it has like one.
Well, no, that's not. It's not that the tree's not empty.
Like
well, actually, that is one precondition. You can't rem root from an empty tree, but there's actually that is one of them. But that's not the whole story. How can you remember what's the precondition for a rem root? Like here, if the tree is like this, can you rem the root?
No.
No. So it has to either be what? Like this or what? Like this. So one precondition, yeah, so you were right. One precondition is that the tree can't be empty. You can't rem root from an empty tree. But there's another precondition.
It can't have two children.
It can't have two children, because if you rem root with two children, what would you do with the one that got, you wouldn't know which one. So if you rem root, if the right child is empty, then the left child becomes the new tree, and if the left child is empty, the right child becomes a new tree. Yeah, oh, that's an important point. So there's actually two preconditions. Okay, so here's a tip. You know then that one of the ways that you check for the precondition violation is when you are in the which node? The empty node. So that's one kind of precondition violation. But the other kind of precondition violation is going to have to be implemented in where? In the non-empty node. Are you with me? Now watch this, you guys. Here comes some interesting logic. The most concise way to do this is to have only one test for the left being empty or non-empty, and one test for the right tree being empty or non-empty. And that's it. Why should you have compound tests? And why should you test if the left is empty more than once? Now let's think about this. I'm going to give you a tip here. Check this out. If the left is empty, What do you know right off the bat if the left is empty? And we are in a non-empty node. What do you know right off the bat? You can do what?
Is like the precondition already fulfilled?
You can.
No, hold on. We are in the precondition for the tree itself being empty has been implemented in the empty node. Now we are in the non-empty node.
But do we know that there's only one node that exists? Like, do we know that?
We have an underscore left and an underscore right.
We don't know.
Hold on, we have an underscore left and an underscore right. We don't know whether they're empty or not.
Okay.
What I'm saying is, if the left is empty, what do you know?
You know that the right must not.
No, you don't know that the right must not be empty, but
You know that it doesn't have to.
It has
wait, is it legal? If the left is empty, do you know that what you're trying to do is legal?
No. Because it
I beg to differ.
Oh, wait, wait.
Yeah, if the left is empty, you don't know if the right is empty or not.
Yeah, I know, but you can do it if the right is empty.
Remove yourself.
No. Oh, this is interesting. Aha. Check this out. Here's 50. All right. Can you rem root 50?
Yes.
Yes. Well, of course. You get the empty tree.
Oh.
You can't rem root from an empty tree, but you can rem root from, if you can rem root this, and you should get the what?
Empty tree.
The empty tree. Now, is everybody clear on that?
Yes.
So now I ask you again, suppose you say if left is empty. If you say if left is empty,
You definitely can.
you definitely can do it regardless of whether the right is empty or not. Are you with me? Because if the right is empty, you're just removing this, but it becomes the empty tree. Are you with me? Is everybody clear? So what you do, if the left is empty, then you bring the right up. You know, you bring the right tree up. Does everybody see what we're saying?
Bring it up.
Well, you know, you got to bypass, you know, you got to take the root and attach it to the right and
And even if
delete.
the right is empty,
And even if the right is empty, it's the same code.
you're still.
I'll show you in a minute. I'll show you in a minute. Let's just go with the high level logic here. If the left is empty, you bring the right up. Now watch this. Else, if the right is empty.
Then you move the left.
Do you know that you can bring the left one up?
Yes.
In fact, at this point, you actually know that the left one is what?
Empty.
No, at this point right here, you know that it's what? That it's not empty. Are you with me? So you actually you even know more in this case than you do in this case. Right. So here, so you do what?
Bring the right.
Bring the left one up. Now watch this. Else, what do you know? The only way to get to this else is if this is what? This is false and what? This is false. So what do you know?
You can't condition.
You know that they are both what? Empty. So here's where you do what?
You like clear it.
Implement your what? Your precondition violation. The else precondition violation. And look at this. There's only one test for the left being empty, and there's only one test for the right being empty. You don't have to say, if this is empty and this is not empty, or if this is not empty and this one is empty and this is not empty, blah, blah, blah. Get hung up with all that. Concise. So now the question is, how do you bring a tree up? How do you bring one up? So what we're doing in here, so what I have in here in figure 8.40 is, suppose the original tree has, suppose we're in the situation where we want to bring the, what are we trying to do here? We're bringing the right one up, yeah? So this would be what we're doing in this situation, the figure. So if this is the original tree, how do we do that? Well, first what we have to do is we have to take the owner and have its underscore what? Root point to the what? To our underscore right root. To our right's root.
Right, but are you sure that it's a precondition violation?
I'm sure, yeah, it's a precondition because the only way you can get here is if there is a non-empty left tree and a non-empty right tree. Because the only way you can get here, this has to be the only way to get here. This has to be false and this has to be false, because if either one of them is true. Oh, and by the way, if you put your return right here, you put your returns. You can put your returns right in here. See, look how concise that is. Okay, so anyway, getting back to the figure. In figure B, so we link the owner, and then the next thing we have to do is nothing. Ha ha. Because we are using shared pointers, and automatic garbage collection takes over again. Because the reference count of that non-empty node comes to 0, and it is automatically garbage collected. Without shared pointers, the programmer would have to be involved in very careful and detailed destruction and removal of the nodes that are no longer accessible. So that's how to do remroot. And this is the most economic, this is the most concise way to do it. Yeah.
Is an empty tree, does it have a root
That is a good
points to it?
That is a really good question. That is a really good question, and we need to make sure that we get that. The answer is the empty tree looks like this.
Okay.
It's this. This is not null pointer anymore. Not in the composite state pattern. It points to an empty node.
Okay.
Yeah. And furthermore, polymorphically, when you do polymorphic dispatch, the empty node code executes when you need it to execute.
Right.
For whatever method. Is everybody clear? Yeah, that was a good reminder. Yeah? And in fact, that's it. That's all I have for by tree C. So there's a hint for remroot. Remroot's going to be an important one. We're going to use it a lot, even in the future. Yeah, question?
on equals?
Yes.
And then equals helper.
Yes, equals and equals helper.
Once you go through the first case, then you jump down into equals helper.
Yes.
Do you then go back through equals helper, or do you have to jump back up into just the regular equals function?
Okay, that's a good question. And the answer is the latter, what you said.
Go back up.
So let's take a look here at figure 8.32C. I think this is going to answer your question. In 8.32C, we are in the non-empty node of the helper. Are you with me? We are in the non-empty node of the helper. And so because we are in a non-empty node, what do we have access to? We have access to underscore left, underscore data, and underscore right, because they are our attributes. They are our data members. In C++, these are called data members. They're called instance variables. They have so many names. I mean, those things. But anyway, they are attributes. Underscore left, underscore data, underscore right. Those are our attributes. And also what we have is we have data and left and right that were passed as parameters. Are you with me? So first of all, you know right off the bat that if underscore data and data are not equal, you know right off the bat that you should do what?
Return false.
Return false. So that's the first thing you should check. Otherwise, what do you have to return? Otherwise, how can these two trees be equal? Well, what has to happen is underscore left has to do what? It has to be equal to what? Underscore left has to be equal to what? To left. And underscore right has to be what? Equal to right. But underscore left and left are both what? Trees. So to answer your question, you do the tree equals.
But do you say an equals helper, or you go back?
No. There's no helper. There's no nothing. It's the equals. If you say alpha and beta, what happens is it first does alpha, and if that's false, it doesn't do this. That short circuit evaluation. But if it is true, then it will do this one, and then if this is true, then this whole thing will be true. Otherwise, this whole thing will be false. But it's you want them both to be. Yeah.
So with the whole equals, you start with just normal equals, then you do equals helper, and then you go back to normal equals.
Well, but from here,
You go back to normal equals,
yeah.
which then puts you back into equals.
Oh yeah, and that'll run through the whole thing.
Between the two.
Yeah. The calling sequence will do that. Sure, recursively. Yeah. Recursively, it's going to go back and do all that stuff, of course. But I mean, conceptually, you don't have to think about that
Yeah, but
when you're coding,
so,
All right. Well, if there's no more questions, then what's coming up next is the what?
CSV.
The composite state visitor pattern, right? Now, of course, so in the same way that we did the composite state visitor pattern for the list, and it was based on the composite state pattern, the composite state visitor pattern for the binary tree is going to be based on the composite state pattern of the binary tree. So the name of our project, the name of this next project is going to be BiTree CSV. So the composite state binary tree with the visitor pattern. It's the BiTree CSV. But look, you guys, we've seen all of this stuff before. Let's recall now what the visitor pattern is. Do you remember what problem does the visitor pattern solve? We want to be able to do what?
Add extra methods.
Add extra capability without doing what? Recompiling. So who are the three people involved in this scenario? There's three people involved. There's the developers of the host. All right, so the host system, and they provide like a product. That's the product that is supplied to the general public with this plugin architecture. And then there are the developers of the plugin who write software that they want to sell to customers to plug into this to provide extra functionality or additional functionality without having to have the host company recompile to integrate that capability into it. And then the third person is the user who buys the plugin and actually executes the plugin. And so the host system provides a minimal complete set of operations that any plugin developer can use to build the desired plugin. Right? So all of this is review. And furthermore, the host provides an abstract visitor class. And who is the abstract visitor class for? When the host provides the abstract visitor class, is he providing that for the user or for the plugin developer? The plugin developer. Right? So the plugin developer uses those that abstract visitor class. And then the host also provides a public method named accept. But that accept is not for the developer, that's for whom? That's for the end user of the plugin. The end user's software is what calls accept. So think of it that way. All right? And so the plugin developer writes a plugin by declaring a visitor to be a subclass of the abstract visitor class. And the plugin developer implements the visitor methods that the abstract visitor class provides. All right? And the plugin user, now so how does the plugin user use it? The plugin user instantiates a specific visitor object. So to use this functionality, you have to set up your own little visitor, and then accept all. What type does accept always take? Accept always takes a visitor as a parameter. Yeah, it always takes, it gets, the visitor gets passed as a parameter to accept, and then the host executes accept. But then what is the code for accept? The accept in turn executes the what? Because the accept it took what? The visitor, so accept uses the visitor to execute the visitor methods that the plugin developer wrote. Okay, so you remember that's the idea. So this is all reinforcement. So here is our same picture that we had before. Does this look familiar? Only this time, instead of it saying instead of saying it list CSV, it's what? By tree CSV. And what does a by tree CSV have? It has a what? What is this one attribute? Underscore root, which is a what to a what? Pointer to an abstract node, so that's just like before, right? Just like what we're doing now, what you're handing in tonight, right? And so there's that class composition because it has an abstract node, but then an abstract node doesn't implement any of these methods. Instead, what happens is, now is this non-empty CS node and empty CS node, is that in the host?
Yes.
It is, okay? And in fact, a non-empty CS node inherits from the abstract CS node, and an empty CS node inherits from an abstract CS node. And then a non-empty node has a what? What three things does a non-empty node have? Underscore left, underscore data, underscore right. They're all private, and so whoosh, it goes back to there. So that host system, that is just like what we did with the by tree CS that we're doing right now. All right, so that's the host system, and then now it's the plugin uses the abstract visitor class, right? Empty is just going to be, if we want to know if a binary tree is empty, well, we're just going to have an empty visitor. Clear, we're just going to have a clear visitor. Max, we're just going to have a max visitor, and so on. Right? So a lot of these things that were done before in the host system are now just done as plugins. So here is a close-up view of the host system, and we can see. So check out. Not only do we have copy root, insert left, operator gets, rem root, right, root, and set tree, we also have what are those two ones up at the beginning that start with an A that are so important? Accept. And accept, what does it take as a parameter? A what? An abstract visitor, and a by tree CSV viz. Right? So accept takes a visitor as a parameter, right? And furthermore, what methods does a plugin developer have to implement to write the plugin for the user? He has to implement what methods? Empty case and non-empty case.
Or non-constant and constant.
For both constant and non-constant. So the ones that are mutable, the constant ones, you just implement the precondition. Right. Otherwise, they're the same. It's the same code. All right.
So the constant versions is to protect against mutability.
The constant versions are C++. It's necessary in C++ because you don't know if the user's data structure is going to be declared to be a constant data structure or not. Are you with me? And a data structure and a type that is const and a type that is not const are not type compatible. So we overload, and we use function overloading, and the compiler can tell, oh, if it's a constant, I'll use this one. If it's not, I'll use this one. But it needs both of them. You see, we can't have, you see what I'm saying? That's so that the user, this is so that the user will have the ability to declare both constant and non-constant binary trees, data structures. Yeah. Yeah, I tell you, this const thing, you know, like I say, I have this love-hate relationship with C++. Man, you can just do anything with it, and it's really efficient, and it's really fast, and it's got so many features that you can do anything in the world you want to do, you can do it. But man, is it complicated. I mean, and all this const stuff is really, it can get really complicated. It's not a small language. Okay, is everybody clear on this? And of course, all these things are templatized with type T, C++ template type T. Okay, and what do we notice that isEmpty has as an attribute? Because isEmpty for just the composite state version of the binary tree, does it have a parameter? It doesn't, because you can just you just say if my tree dot is empty, no parameter, right? But what does it do? Is it void or non-void? Is empty.
Non-void.
It's non-void because what does it do? It returns a what? It returns a Boolean. So what we have to have is, in the attribute of our isEmpty visitor, we have to have an underscore result, which corresponds to that returned value. Same way with this max. Okay, that's why we have that extra attribute. Okay? So, first observation is that the primitive methods for bytree CSV are implemented exactly as they are for bytree CS. And you guys, here is the code for accept. Now, do you remember, does this look familiar? So let's take a look. Let's analyze this one more time. Okay, so first of all, the user is going to have a visitor, and the user is going to pass that visitor to accept. Right? So what does the binary tree CSV version of accept do? You see, it takes a visitor as a parameter, and what does it do? Once and for all for our developers and users. It calls the what? The root version of it. So now we don't have to the developers don't have to do that anymore, because that's done once in the what? In the host by accept. And furthermore, whether the user needs it or not, what does the what does the tree version pass along to the root as its first parameter?
This.
Star this. And is star this the actual parameter or the formal parameter?
Actual.
It's the actual parameter. And what formal parameter does it correspond to? Owner. Now that's the way it is here. The formal parameter in the plugin, we're going to name it host. And now you guys, let's take a look at what the node version does of accept. What does the empty CSV node version of accept do? It takes this visitor, which is in this parameter, and what does it do? Look over here. To here, what does it do? It uses it to execute its methods. Now, do you remember how this works? Because this visitor has methods that got pre-compiled for the empty case and the non-empty case. And so it does visitor.emptyCase. But where's that code? Where did that code for the visitor come from? It came from whom? The plugin developer. And so it's executing code that did not need to be compiled with the host. Now that's the key idea again. Is this more Becoming more familiar? Okay, all right. And the same way with the non-empty. So the non-empty node version of accept just takes the visitor and does visitor.nonempty case owner. All right. So now, when you write a plugin for a binary tree, the BiTree CSV project, you have here's the 6 things you have to work with. This is your tool kit. This is the little tools in your belt, right? You got 6 things to work with. So first of all, to access the parts of a binary tree, you will always have the host. And how do you get to those 3 parts of the tree? You have access to you have root. Root is a function, right? It's a method. So you have the host's root, you have the host's left, and you have the host's right. Are you with me? So that's how you access the parts of a tree. Now, to build a binary tree, if you want to change it, then the way you change a binary, there's 2 ways to build a binary tree, to make it bigger. You have insert root, and you have set tree. Remember how set tree worked? Okay? So you got insert root and set tree. And the only way to trim a binary tree, in other words, to get rid of part of it, you have one thing, and that's what? Rem root. And trust me, you can do anything with any binary tree with just these 6 things. This is a minimal complete set of methods. A minimal complete set. You can do anything with, and we will do lots of stuff. We'll do lots of stuff with these. Even in a future project, we will use this visitor method pattern. Well, we will use this code. Okay, so those are the 6 things that you can do, that you need. And the current version of the DP4DS distribution software differs from the previous versions in 2 respects with this BiTree CSV project. First, we now have 8 methods that the host provides instead of 6, and also the implementation of remroot in the previous version of the software distribution used isEmpty, which was a plugin, so that the host can be self-contained and can be implemented without any plugins. The current version of the DP4DS distribution implements remroot without using the isEmpty plugin. Instead, it uses 2 helper methods, left remroot and right remroot, which use polymorphic dispatch instead of using the isEmpty plugin. And the implementation of remroot is an exercise for the student. So left remroot and right remroot are 2 private helper methods whose sole purpose is to implement remroot. The calling sequence is as follows. Remroot calls left remroot, and then left remroot in turn calls right remroot. So left remroot and right remroot are not just mirror images of each other, they do two significantly different things. The next figure is the code for remroot. The precondition of remroot is that this tree is not empty, because you cannot remove the root of an empty tree. And another precondition is that the root of this tree has at least one empty child, because if both children are non-empty and you remove the root, you would have 2 trees left over, and which one would become the new tree. Then the postcondition is that the root node is removed from this tree and its element is returned. So now, as usual, the tree version of remroot calls the node version of remroot, and it passes star this as the actual parameter corresponding to owner as the formal parameter. Now, if this tree is empty, then the empty node version is called, and that empty node version implements the precondition violation. On the other hand, if this tree is not empty, the tree version of remroot calls the non-empty node version of remroot because this tree is not empty. And furthermore, it passes along star this as the actual parameter corresponding to owner as the formal parameter. And we have a little note here that owner is the parent tree of underscore left. So the non-empty node version calls underscore left arrow left remroot owner, passing along the owner. And because it's calling underscore left arrow left remroot, that takes us into the environment of the left subtree of the original tree. So now let's take a look at the left remroot code. So here we see that the precondition is that the parent has at least one empty subtree, and the postcondition is that the root of the parent is removed and returned. And another little note that this is a helper for remroot. Now, we are in the environment of the left subtree of the original tree. And as usual, the tree version calls the node version. So the tree version calls underscore root arrow left remroot star this and parent. So star this is the actual parameter that corresponds to owner, and parent gets passed along as parent. Now, if the left subtree is empty, then the empty CSV node version gets called, and we know that because the left subtree is empty, we can immediately remove the root. And if that is the case, there is no call to right remroot. On the other hand, if the left subtree is not empty, then the non-empty CSV node version will be called, and it will in turn call right remroot. But now how does it do the call? It calls parent.right arrow right remroot passing along the parent. So that will take us to the environment of the right subtree of the original tree, which will have access to parent because it got passed along as a parameter. So now here is the code for right remroot. Now, the precondition for right remroot is that the left subtree of the parent is not empty. Now, do you see that this precondition is automatically satisfied by the calling sequence? So we don't need any code in this right remroot to test for the violation of the first precondition. The reason that we know that the left subtree is not empty is because it got called by the non-empty node version of the left subtree. On the other hand, the second precondition is that the right subtree of the parent is empty. So that precondition needs to be implemented in this code. The postcondition is that the root of the parent is removed and returned. And here again we have a little note that this is a helper for remroot. So, as usual, what happens is the tree version of right remroot calls the node version of right remroot, passing along star this as the actual parameter to owner as the formal parameter, and passing along parent as parent. And now the two node versions are exercises for the student. One of these will be a precondition violation, and another one will be the actual removal of the root. Now this figure is a visualization of the call sequence of remroot for an empty left subtree and a non-empty right subtree. So in item number 1 in the figure, the tree remroot calls the non-empty node version of remroot because this tree is not empty. Then the non-empty node version of remroot calls the left tree left remroot, which takes us to the environment of the left subtree, which is an empty tree. Then, as usual, item number 3, the tree left remroot calls the empty node version of the left remroot because this is the case when the left tree is empty. And in item number 4, the empty node left remroot removes the root. And in this case,
right rem root never gets called. On the other hand, the next figure shows a trace when the left subtree of this tree is not empty and the right subtree is empty. So again, starting at item number 1, the tree rem root calls the non-empty node version of rem root because this original tree is not empty. Then in item number 2, the non-empty node rem root calls the left tree left rem root, which takes us into the environment of the left subtree. In item number 3, we are in the environment of the left subtree. And the tree left rem root calls the non-empty node version of left rem root, this time because this tree is not empty. Then the non-empty node version of left rem root calls the parent's right rem root, passing along the parent. And in item number 5 now, we are in the environment of the right subtree of the original tree, and we have access to the parent. And the tree right rem root calls the empty node version of right root because this tree is empty. And now the empty node version of right rem root actually removes the root.
And so a plugin is a subclass of an abstract visitor. Okay, so and because it's a subclass, we're free to add any number of attributes of any type. And that's how we do the parameters. That's how what used to correspond to parameters now are attributes. So this is all familiar, this is all review. And so here's our translation techniques. This is all the same as we had before. The input parameters in the native methods are attributes in the visitor, initialized in the constructor for the visitor. The output parameters in the native method are reference variables, and the non-void methods have that extra little underscore result. Okay, and we have to provide a extra little result method. And we will start off with the by tcsv is empty viz. I tell you, we wanted to make these names unique. It was kind of hard. So the by tree CS version of is empty is non-void, therefore the visitor version provides a result method. Now, do you guys remember how this code is going to look? It's going to look identical to what we did before. So to use a visitor for a non-void method, you have to declare a local visitor. You pass it a parameter in the data structures accept method. You call the visitor's result method to get the result of the computation. So that's all. We've done this before. And here is the by tcsv is empty viz. And what attribute does it have? Underscore result, which is type Boolean. And why is that? That's because it's non-void, and so we're going to have to return that. Okay. And in the constructor, we don't have to initialize anything in the constructor. And by the way, now let's take a look at the empty case. Now, what is the name of our parameter here? It's host. So now it's known as, that's a common name in this visitor pattern thing. So we're going to call it corresponds to owner, right? So it's host. And basically, in the empty case, that's all we do is we set underscore result to true. And in the non-empty case, we set underscore result to false. All right? And then, because it is non-void, we have to provide this extra little method called result. And basically what it does is it returns underscore result. And then, here is our global function for convenience. All right? So, using this global function, we can say this. We can say if, parentheses, is empty, parentheses, my tree. So this is how we use the convenience function. So notice that we do not use the convenience function this way. We do not say my tree dot is empty. Is everybody clear on that? Okay, we don't do this anymore because this is not a method. It's a global convenience function, right? And so when we say if is empty, what happens? We call is empty, and then this is like my tree. So this is, so what is this saying? This is saying, and so my tree would be the what? Which parameter, actual or formal? Actual, and tree is the formal parameter. So we're saying what? My tree CSV is empty viz is the type, and here's our little local visitor is empty viz. And then we do this tree.accept, which is like saying my tree.accept, right? Tree.accept. And what does accept we pass along to accept? A visitor, okay, whose methods get executed. And then we call this result method right up here to return. So we say return is empty viz.result. And that's is empty. And all this is familiar because we've all seen it before. But now it's a little trickier. I mean, it's going to be a little bit different. The code's going to be a little bit different. But the whole idea of the visitor pattern now we've done. And so this should reinforce what we learned before. All right, good deal. Let's go have a good weekend.